Before we start, just a comment that sometimes the badges are kind of annoying, but it's nice to have so that when we talk to each other, we know who's who. So one of the things of the school besides learning is meeting people, not only you and the professors, but between you. So I think it's nice to be wearing a badge.
Okay, so we're ready. So any pressing questions on anything? Okay, so let me just remind you of where we were yesterday. We were talking about measurements of neutrinos coming from the sun, and the main important message that you want, or there are two really important messages. One is that we do get to see neutrinos from the sun, which by itself is a really big deal. And the other thing, which is very important, is that until the end of the last century, we had this thing called the solar neutrino problem, or the solar neutrino puzzle, depending on who you ask. And the puzzle had to do with the fact that we would measure neutrinos coming from the sun using different techniques, and we would always get fewer neutrinos than we anticipated. So that's the problem. And we're looking at this problem in a little bit more detail. And let me just remind you, all of the information is included in this plot. And let me just remind you that if you ignore the two bars on the right-hand side and just look at the stuff on the left-hand side, effectively what we were doing is we were measuring neutrinos coming from the sun in two qualitatively different ways. And I want to emphasize this today because we want to try to understand what the possible solution to the problem is. So one way is these are radiochemical experiments, right? And I said that the way they work is that a neutrino comes in, it hits some nucleus, and then it undergoes some induced beta decay, if you want to think about it that way. So you have something that looks like this. So this, for example, is how the chlorine experiment works, and the germanium experiments work in the same way, where you're turning gallium into a germanium. So these are called the gallium experiments. Now what's very, very important, and there's sort of a caveat about the way you make this measurement, is that in order for this measurement to happen, this neutrino here has to be what we call an electron neutrino, right? Because it's the electron neutrino that knows how to make electrons. If you had a muon neutrino coming in, it would only be able to drive this reaction if you could produce a muon here in the final state. But you can't do that because you don't have enough energy. The energy of these neutrinos is not big enough to produce a muon. Again, the kind of number you want to remember is these neutrinos from the sun have energies below 10 MeV, and the muon mass is 105 or 106 MeV. So clearly not enough energy to do that. The other experiment is this water detectors, both the Kameoka experiment and the super Kameoka experiment. They measure the neutrinos via neutrino electron scattering. And this is an elastic scattering process. So you measure this reaction over here. And the thing that you get to see in the experiment is the electron. And again, the reason they see that is because at low energies, the neutrino can only hit the electrons in the tank. The other thing, so remember, this is a water tank. If you remember, water has hydrogen and oxygen. So you can ask yourself, what happens when the neutrino tries to hit an oxygen? It does know how to do that, but if it does that in an elastic way, that's a really, really boring reaction because you're basically hitting a big nucleus with a neutrino. The nucleus is happy to recoil a little bit, but the detector is completely blind to that. So a very small recoil to an oxygen nucleus is totally blind. You can ask an interesting question, which is, why can't I transform oxygen into some other nucleus? Why can't I do the equivalent of that with oxygen? And the reason is that oxygen is a very, very tightly bound nucleus. So in order to convert oxygen into something else, you have to provide a lot of energy, and these 10 MeV of energy that the neutrino carries along is not enough to convert the oxygen into anything useful. I guess another thing you want to keep in mind is the other picture you could have in your head is that maybe the neutrino can come in, hit a proton inside of the oxygen and knock the proton out. That can happen, but that can't happen at these very, very low energies. So the energy of the neutrino is very important to determine how you get to see the neutrino in your experiment. Now coming back to this neutrino electron scattering, which is an elastic process. Yeah. Can it hit with the what? The rocks? Yes, it can, but the detector doesn't get to see that. So there's a lot of other material around. So you have, for example, the stuff that makes up the cavern. So the neutrino could hit there. That's mostly silicon and oxygen and other stuff. You don't get to see the effects of that because it would require the products of the reaction to come into your detector and to come into your detector in a way that leaves a signal, and you really don't have any of that. But it is things that you worry about. So you don't want to make the detection that way for solar neutrinos, but you want to make sure that nothing screws up your measurement that's coming from the outside. So oftentimes what you do is you make sure that you only look inside of your tank and you exclude stuff that's happening very close to the edges of the experiment. That's one very, very standard technique of both neutrino experiments and dark matter experiments, and all kinds of other experiments as well, that oftentimes your experiment has a certain size, but you only look inside a volume within your volume just to make sure that there's nothing leaking into your detector and giving you a false signal. So this is something that you hear about a lot, I assume, next week, talking about detectors. And it's a very important thing when you read papers and you try to estimate what experiments can do. They will often tell you, oh, I have a detector which is 50 kilotons. That's a super Kameoka detector. But the use volume of the detector is half of that. It's called the fiducial volume. So the fiducial volume is a fraction of the total volume, and that's the volume that you care about. And sometimes, so for some of the dark matter experiments, sometimes they will cut really hard, and maybe you have a volume that's this big, but the volume that you actually analyze the data for is a very small subset of that, just to make absolutely sure that there's nothing funny going on from the walls. Okay. All right, so this is the signal that you see in these water experiments. The reason I'm pausing and talking about this in a little bit more detail is that which neutrino knows how to do that? So what's the flavor of this neutrino? The electron neutrino can do that, but can the muon neutrino do this? Yes, right? Because it's a neutral current reaction. So this is true for all of the neutrinos. Well, let me write them separately like that. So these are the two processes that can happen. The tau neutrino, turns out, does the same thing that the muon neutrino does. Now, the one thing which is very important is that this cross-section turns out to be way bigger than that one. Okay, and I'll just remind you of why that is, or I'll tell you why it is if you don't know. First of all, that's not an obvious statement at all. But you can certainly very, very easily convince yourself that cross-section is different from that one. And that has to do with the fact that if you wanted to calculate this, and if you know about Feynman diagrams and the weak interactions, the leading order contribution to this process here is something that looks like this. So here I have, say, a neutrino. It exchanges a Z boson with the electron. And that's a physics process that the electron neutrino, the muon neutrino, and the tau neutrino can see. So this contribution here for the cross-section is the same for everybody. But the electron neutrino has an extra contribution, which is it can do this. So remember, this is neutrino electron scattering. But this guy can turn into an electron. This guy can turn into a neutrino. This is a W exchange diagram. And this one is special to the electron neutrino. So if you wanted to calculate this cross-section, you would calculate this amplitude. You would add to this amplitude here. Then you would square that to get the cross-section. So this complex number squared is clearly, or it's easy to believe that it's going to be different from this complex number by itself squared. Okay? Now it's not clear which one is going to be bigger, because it could be that these interfere, it could be that one is much bigger than the other, and so on. So it turns out that this contribution here will dominate, and it will make the cross-section for neutrino electron scattering bigger. Okay, so is that very, very clear? By the way, you can do anti-neutrino electron scattering, which we're not doing, but if you were to do that, the anti-neutrino electron scattering, if it's an electron anti-neutrino, has an extra contribution. That's not this one. This one is not there for the anti-neutrino, but there's going to be an S-channel W exchange diagram as opposed to a T-channel W exchange diagram. Yeah. You don't distinguish them. So from the experimental point of view, they look exactly the same because all you see is an electron. But I do know that the cross sections are different. So that means if I have 100 neutrinos coming in, if they're all electron neutrinos, I should see a certain number of scattering events. If they're muon neutrino, I see a different number of scattering events. By the way, if you're very picky, the energy distribution of the electrons in the collision is different from muon neutrinos and electron neutrinos for the same reason. So this is not just a statement about the total cross-section, but the differential cross-sections are a little bit different as well. So in principle, if you could measure the differential cross-section, you could tell if it's a muon neutrino or an electron neutrino. In practice, that's very hard to do. You could envision that maybe a particular experiment could do that. Maybe the Bohr-Xeno experiment could do it. Doesn't matter what experiment that is, but that hasn't been done, and it's not something that we need to worry about. Okay, so the reason I'm talking about this is to say, when we go back to this picture here, hopefully, you see fewer neutrinos from the sun than you expected. And the question then becomes, what did we do wrong? Why are we getting the wrong answer? And like I said, I mentioned the two simplest logical possibilities for what's going on. One possibility is that so you're looking at this plot. There's a left-hand column and a right-hand column, and maybe the left-hand column is wrong, which means your solar model calculation is wrong, or maybe your right-hand column is wrong, which means your measurement is wrong, or some combination of the two. And the fact that we did many experiments rules out at some level the possibility that the experiment is wrong. You can do one experiment wrong. You can't do 4 experiments wrong. You can, but that's very, very unlucky. So the other possibility is that the solar model is wrong. And that hypothesis is really, really hard to make work. But it remains a logical possibility. And I think what we'd like to say is that the third possibility is that the neutrinos are wrong. That there's something fundamental about neutrinos that you're getting wrong. And as everybody knows, that turns out to be the right answer. Now, you can see the simplest explanation that you can do that has to do with, in quotes, the neutrinos being wrong, is that when we make these estimates here, we assume that all of the neutrinos that get from the sun to here are electron neutrinos. That's included in all of these calculations. And this is, if you had a muon neutrino, these reactions here don't happen. Even for the electron scattering, if you have a muon neutrino instead of an electron neutrino, the cross-section is different, which means that your prediction will also be wrong. One way of thinking about this is if an electron neutrino behaves like a muon neutrino in the chlorine experiment, it doesn't show up at all. If the electron neutrino behaves like a muon neutrino in the water experiment, it only shows up as 1/5 of an electron neutrino. That's one way of thinking about that. It contributes a little bit, but it doesn't contribute as much as the electron neutrino. So this explanation that it's possible for an electron neutrino to arrive at the Earth as a muon or tau neutrino, that explanation would fit the picture here that we observe fewer neutrinos than we expect because we were treating all of them as electron neutrinos, and maybe that was the hypothesis that was wrong. So what happened then was that somebody built a model to test that hypothesis. Okay, and I'm sorry, not a model, but somebody built an experiment to test that hypothesis, which is a snow experiment. And I'll just say a few words about that, and then I'll show the result. The snow experiment is at Sudbury Neutrino Observatory. That experiment is no longer there. It's in a very deep nickel mine in Canada. But the entire facility was turned into a lab. It's called a snow lab. And there are many, many experiments there, including something called SNOW+. And you can ask me about that later. That's a double beta decay experiment, which could do solar neutrinos as well. But the experiment was designed to test the hypothesis that there are neutrinos other than electron neutrinos arriving from the sun. And the way that they do that is that they propose to measure the flux of neutrinos coming from the sun in 3 different ways. So it's kind of an overkill. We're going to measure the same thing 3 times, and we want to see what answers we get. And the way that they did that is that they built a very large tank of heavy water. So it's ultra pure heavy. And the key thing about heavy water is that heavy water is like regular water, except that instead of hydrogen, you have a deuterium. So that's a proton-neutron bound state. Okay? So that's the SNOW experiment. And basically, it's a big tank of heavy water. A neutrino comes in, and then you can ask, what can the neutrino do in the heavy water? And like I said, the oxygen is totally useless, so we don't care about that. Yes? Yeah. Mm-hmm. So it's that's a very good point. I kind of cheated. It's bound enough that the cross section for the neutrino to come in and break up the oxygen is very, very suppressed by phase space, if you want. And on top of that, the remnants don't give you a signal in the detector. That's the best way of thinking about that. It happens very, very, very rarely. Oh, it's not. It's more rarely than in chlorine, but not infinitely more. But remember, the chlorine experiment is designed to look for the argon. The Super K experiment couldn't care less about oxygen turning into something. It has no ability to see that. Does that answer the question? I mean, that's the, so sorry, yeah, so it's kind of a cheat. Oxygen is not super powerful nucleus, so I didn't want to imply that. I did want to imply that the cross-section is not large because of phase space, because the oxygen is a little bit deep. You know, the oxygen nucleus is doubly magical, if I remember that correctly. So it's 8 plus 8. So it does make it more tightly bound. And on top of that, if you do hit an oxygen and something spectacular happens, you don't get to see any of the results of the collision. That's a very good question, and the answer is always cosmic rays. So these experiments are looking for something very rare, this neutrino interaction, so they have to be very big. That means that they will see a lot of other stuff, and you don't want them to see other stuff. So cosmic rays are a big problem, and they're not a big, so again, people will probably talk about this next week, but the key thing is not just that, so first of all, cosmic rays is just muons. These are muons coming in. The big problem is oftentimes, especially for these low energy experiments and the dark matter experiments, it's not the muon going through your detector that you care about. The muon often looks like a muon, so you wouldn't get confused by that. But it's the muon hitting things outside of your detector, and maybe you have some neutrons that leak into your detector. For a dark matter experiment, that's the kiss of death, basically. So if you have neutrons getting into your detector, you're done. You can't do the experiment. For low energy neutrino experiments, that is a part of that. And then you have to worry about more weird things like neutrons can be absorbed and form weird that then decay out of time. And that gives you something that looks like these neutrino signals. So you're really worried about cosmic rays, and people call it the cosmogenic induced background. And that has to do not just with the cosmic rays themselves, but the cosmic rays hitting something that then gets into your detector and gives you a very hard time. And depending on the type of experiment, this is either a big problem or a not so big problem. So for example, the Super Kameoka experiment is not specially deep. It's inside of a tunnel in Japan, and it's pretty deep, but not super deep, and that's good enough. They do have cosmic rays that they can see in a variety of different ways, and they can live with that. The SNOW experiment is super duper deep because they're more interested in solar neutrinos, so you really are very concerned about these cosmogenic backgrounds. The same is true for many of the dark matter experiments. And for the dark matter experiments, there are other ways of circumventing background, so that guides a little bit of how deep they can be. By the way, the snow experiment is really deep, whatever that means. And it's actually, it's a fun place to go. It's an active nickel mine, and you go down an elevator for a very long time. It's about, almost 2 kilometers deep. And it's a cool place to visit. Anyway, so good. So going back to the snow experiment, it's a heavy water detector. The thing that you care about for the detection is the Deuteron, and that's the thing that was very important for the experiment. So what can the snow experiment measure? It can measure neutrino electron scattering, just like the super Kameoka and the Kameoka experiment can measure. So it sees these reactions here, and as I said, if your electron neutrino was turning into a muon neutrino, you would see fewer electron neutrinos than you expected. So you see an effect. That's one reaction that happens. The other one that happens is, and this one is visible in the heavy water, but it's not visible in super K, is that the neutrino can come in, it can hit this proton-neutron bound state, and then it can have a charge current reaction with the proton, or with the neutron, sorry. So you get an electron plus 2 protons. So that's the other reaction that can happen. And then the third reaction is the neutrino can come in, it can hit this guy here, and then it can just break up the deuteron, like that. Okay? So these are the reactions that can happen, and it turns out that there are many things that you probably know about Deuteron, but if you don't remember any of them, the one thing that's very important for nuclear physics people is that the Deuteron is almost not a stable nucleus. Right, so you probably remember that. You learned this in basic quantum mechanics, hopefully. You can calculate the Deuteron potential depth by saying that it's very loosely bound, if you remember pretty basic. So that doesn't matter. But the Deuteron is very easy to break up. If you've ever studied, for example, a Big Bang nucleosynthesis, the Deuteron is important for the calculation and the numbers that you see, and the fact that it's easy to break up kind of delays Big Bang nucleosynthesis from a very naive timescale that you would have anticipated for Big Bang nucleosynthesis. For our purposes, it means that for these solar neutrinos, the Deuteron can be broken up in a way that my detector can see what's going on. So these are the 3 reactions that the snow experiment can see. And like I said, this one here, the electron neutrino contributes, but the muon and tau neutrinos would also contribute. For this reaction here, only the electron neutrino knows how to do this because the electron neutrino is turning into an electron. And for this reaction here, everybody contributes in the same way because this is a pure neutral current reaction. The only diagram that contributes to this, if you want, is this one, where here you have a proton or a neutron. It goes this way, okay? And these reactions have a name. So this is called elastic scattering. This is a charge current reaction, and this is a neutral current reaction. And the reason this is a very clever idea is because it can give you a definitive test of whether there are neutrinos other than nu E coming from the sun. Because again, the flavor of the neutrino will impact the relative rates of these 3 ways of measuring the flux of neutrinos from the sun. So that's the snow experiment. And if you want to go into the history of that, they actually measured this particular reaction in 3 different ways, just to be very, very sure that they knew what they were doing. By the way, this reaction here is the one that you should, so, by the way, what do they measure? They can measure the electron. So that's just like when the water Cherenkov detectors. And they can't see these protons at all. These protons are totally useless, but they can see the neutron. So what happens is, just like I talked about in the reactor neutrino experiments, neutrons will eventually be absorbed by something, and they will give you a signal. Here there's no delayed signal because there's no electron, but you get a neutron signal. So as long as your detector is clean enough and quiet enough, you can see this neutron signal. And that measurement is hard. And the way that they did this measurement was in 3 different ways. And I'll just say this very quickly. One way was just hoping that this neutron would be absorbed by whatever was in the heavy water and would give you a photon signal that way. And that gives you a very faint signal for detecting the neutrons, but it works. The next thing that they did is they dumped salt into their detector, and they had a lot of chlorine in the water, and the chlorine has a larger cross-section for absorbing the neutrons, and that gave you a bigger signal for seeing neutrons. The reason they didn't do that first is because you're very, very afraid of dumping anything into your really clean detector. So this is a big impurity in your detector, and they wanted to make sure that they could put the salt in, they would get the salt out, and it turns out that all of these liquid detectors, or that's not true, but this particular liquid detector is filtered, so the water is always being cleaned up. So the challenge for putting the salt in was that when you filtered it out, it would filter the chlorine out. So you have to keep pumping the chlorine back in as well. And then the third thing that they did is that they invented, in quotes, a neutron detector, which was they created these tubes with a helium-3 inside. And helium-3 has a gigantic cross-section for absorbing neutrons. That's easy to see. Helium-3 is a weird nucleus. It doesn't like to exist as helium-3. If you give it a neutron, it's much happier because helium-4 is a very, very stable nucleus. So the cross-section for absorbing that is very high. And the idea is when you would detect a signal inside of these rods that were sitting inside of the tank. That's the thing that they did last, because it meant you had to install these detectors inside of your very, very pure heavy water. And it's a really fun experiment. It's no longer taking data. It's actually not there anymore. Like I said, it's a heavy water experiment. You can ask yourself, how do I get a lot of heavy water? It turns out that nuclear reactors like heavy water. So they borrowed the heavy water from the Canadian government. They had a contract for a lot of money where they promised that they would return all of the heavy water that they borrowed. And that's all of the heavy water that they borrowed. And it turns out, just for fun, that they actually returned more heavy water than they got to begin with. That's a true statement. Now, they weren't making any heavy water, but it's just that they measured it more precisely than the amount of heavy water that was delivered to them. And it turned out that it was the right number was a little bit more than the company had specified. There's another fun, yes? Here and here? Yes, that's a very good question. I forgot to say that. So the question is, how can you tell this signal from that signal? Because the signal here is an electron, and the signal here is an electron. So that doesn't look like you can tell these signals apart. That's a very good question. The way that you tell it apart is by the kinematics. And the main thing is, I mentioned this before, for neutrino electron scattering, the electron tends to go in the same direction that the neutrino goes. For this reaction here, it turns out that that statement is not true. The electron doesn't particularly care to go in the same direction that the neutrino is coming from. And in fact, the electron has a tendency to go back. So it goes, the cross-section peaks slightly in the opposite direction from where the neutrino is coming from. So when they do the fit, of course, they look at the electron candidate spectra, and then they do a fit for this combination combined with that combination. And the kinematics are different enough that they can tell the difference. And for here, the signal is only the neutron. Okay? Oh yeah, the other thing I forgot to say, I said that they made these helium-3 counters. And you can ask yourself, how do you get a lot of helium-3? And I won't tell you what the answer is, but it's really hard. There's no place you can go where you say, oh, here's a lot of helium-3, I'll just go and take it to the lab. And the helium-3 is a hard substance to find. Condensed matter, people like helium-3 a lot because it's a funny substance when you make it really cold. So they do a lot of research with helium-3. You know, their experiments are this big. These experiments are gigantic, so it's a different order of magnitude in how much helium you need. Okay, so this is the result of the SNOW experiment. This is a very, very famous plot. I will remind you that the SNOW experiment also got the Nobel Prize for this measurement. So it's this plot right here. This is a slightly older version of the more recent plot. So what this is because they're making these 3 measurements, they can make an independent fit to the electron neutrino flux and the flux of other neutrinos coming from the sun, muon or tau. And because these reactions here measure different components of the flux, they translate into different curves in this plot. By the way, understanding this plot is one of the homework problems that I'll give you tonight. But it's a really cool plot because you see the charge current measurement is a vertical line because it only sees the electron neutrinos coming from the sun. The elastic scattering is the green band. It's mostly a horizontal line, but not quite, because it sees mostly the electron neutrinos, but the muon and tau neutrinos contribute as well. So it tilts the line a little bit. And then the blue curve is the neutral current measurement. And the neutral current measurement measures all of the neutrinos at the same time. So that gives you a different straight line of the type, x plus y equals a constant. And that's why you get this blue line. And there are many, many impressive things going on in this plot. The dotted lines indicate the calculations of the standard solar model when you're kind of agnostic about the neutrino flavor. So you see that the blue line and the area between the dotted lines agree perfectly. That means that the calculation was right, whatever that means. The other thing that's very impressive is that those three measurements meet at a point. That means that whatever they're measuring is consistent, right? So there's no big screw up experimentally, and it's not a different, and the hypothesis that they raised is not incorrect, because you have three lines meeting at a point, which means that things are working out very well. And of course, the really important result is that if you look at the vertical scale, you get a non-zero value for the flux of muon and tau neutrinos coming from the sun. So the conclusion is, at the end of the day, that somehow there are muon and tau neutrinos coming from the sun. That's what this experiment established. Okay, and we're not talking about how that happened. We're just saying that you do the measurement, and that's what the measurement is saying. So this is yeah. Yeah. Good. That's a very good question. So the question is, how do we know that the sun only knows how to produce electron neutrinos? And that's an excellent question. And the answer is, we go back to how the sun works and how the neutrinos get produced. And it turns out if we understand how the sun works, all of the neutrinos are produced by charge current weak interactions. Okay, so that's what you want to keep in mind. So it's a charge current, so it's a weak interaction of the type that's related to beta decay. So that means that all of your neutrinos are being produced along with another charged lepton. And what happens then is, as I said at some point, the sun is very cold, so there's not enough energy to produce a muon or a tau. There's just not enough energy. So any charge current process that we observe has to involve the electron. Of course, another thing you can say is that the sun has a lot of electrons. So the electrons can hit stuff and give you charge current reactions as well. Another question you could ask is, how about the neutral currents? There are these Z exchange diagrams that can also produce neutrinos. So in principle, I could have, two protons bang inside of the sun and emit a Z boson, which then decays into two neutrinos, and that would give you a flux of other flavors of neutrinos via neutral current. That rate turns out to be ridiculously small, again, because the sun is really cold. Okay, so it's an excellent question, but if we understand particle physics and if we understand the sun, there's no mechanism that we can envision that will allow you to produce muon or tau neutrinos in the sun. Again, there are physics processes that could do it, but the conditions in the sun are not sufficient for doing that. Yes? Very good. So for other kinds of stars, you have to do the calculation again because the conditions are going to be different. And there are a couple of different things that people know. So they know that the environment in a regular star, as it's evolving in its nice history, most of the time does not allow you to produce neutrinos. Actually, we often use stars to place bounds on other properties of neutrinos. So there are certain stars that if they knew how to produce neutrinos, they would be in trouble. And the reason is the following. if you have an efficient mechanism for producing neutrinos, the neutrinos escape the environment very, very fast, which means that you can lose energy very efficiently, and then your star would not be the star that you think it was. The main exception are supernova explosions and other weird things like these neutron star mergers. But let's just talk about supernova explosions. Supernova explosions are the exception because the temperatures and densities are very, very different. And you do have basically two important phenomena that happen. And I think Fabio talked about this in the questions last time. What happens eventually in the neutron star is that I'll say this in a particle language, but you get the electrons and protons really close to one another. They can fuse into a neutron. That's a weak process. You emit electron neutrinos when that happens. So you have this thing called the deleptonization of the star. That's when you're getting rid of all of the leptons. You convert all the electrons into electron neutrinos. These electron neutrinos are ejected out, or they would try to be ejected out. That produces a lot of neutrinos. That's not most of the neutrinos that are produced in the supernova. Most of the neutrinos are produced by some version of this. So you do have enough energy that your nuclei can radiate off Z bosons, which then decay into neutrino pairs. And that's what happens for so this production of electron neutrinos is very fast. And then you start emitting these neutrinos from Z stratum for a little while. And just to conclude the story is a little bit more interesting or more complicated because I said in something like a red giant, if you could produce neutrinos, the neutrinos would exit very quickly. In the supernova, you produce all these neutrinos, they don't get to exit very quickly because the environment is too dense. So even the neutrinos get trapped. So the neutrinos that come out, they actually come out thermally, like the photons coming out of the star. So they bounce around for a while, and then they come out, and they come out with well, we don't know this because we haven't made that many measurements, but we believe that they should come out with a pseudo-thermal spectrum. It's usually a truncated thermal spectrum, but that doesn't matter. So yeah, so that's a very, very different environment. The sun is not like that. The sun is a very vanilla kind of star. Okay, so this is a snow experiment. So any more questions about that? Again, it's a really cool experiment, and understanding these curves is very easy, and it's something that's worthwhile doing and sitting down and calculating. Okay, so now I want to talk about atmospheric neutrinos. I won't spend too much on this because I've said a lot of the ingredients before. The key thing about atmospheric neutrinos is cosmic rays hitting the atmosphere. Cosmic rays hit the atmosphere all the time, and they produce pions. The pions decay into muons and muon neutrinos. So that means that you have this constant flux of muon neutrinos, and let me back up and say muon neutrinos, and then you have the muons. The muons sometimes will decay, and they will decay into more neutrinos. So that means that there's a bunch of neutrinos, both of the electron flavor and the muon flavor, that are produced in the atmosphere all the time. And of course, the cross-section is very small, so they very, very seldom hit something. But if you build a big detector deep underground, then that detector could see these atmospheric neutrinos. Atmospheric neutrinos were a thing that people talked about, and they designed experiments to see this a long time ago. I can't remember, probably in the 80s already they had seen atmospheric neutrinos. The big contributor to the atmospheric neutrino physics will be the Kameoka experiment and the super Kameoka experiment. And like I said already, let me just remind you of the history of that. This is the name of the first experiment. And the thing you can ask is, where do they get this name? And your answer will be, I know nothing about Japan or Japanese, so that sounds like a pretty plausible Japanese name, end of story, which is a good answer. But it turns out that this is Kameoka is the name of a mountain or a town, mine in Japan. I know it's a town for sure. And I think it's also the name of the mountain, but I can't promise that that's true. So that's the Kameoka Mine. And then this NDE is a nucleon decay experiment. So this is an experiment looking for proton decay. And like I said, what you look for is a proton to decay into something, and you hope to be able to observe what that something is. The typical energies that you care about are of hundreds of MeV, because you're converting 1 GeV, which is the proton mass, into something that you can observe, hopefully. One possibility is that the proton can go into a positron and a pi zero. That's the best thing to look for, because the positron is something the detector knows how to see. The pi zero decays into 2 photons, which the experiment also knows how to see. So it's a great thing to look for. There are other things which are harder to look for, but they look for them anyway. So these types of experiments are very worried about neutrinos produced in the atmosphere, because the neutrinos produced in the atmosphere can go through your experiment. They have energies that go from 100 MeV to 100 GeV, and if they hit something, they will give you an electron or a muon with exactly the kind of energies that you worry about for proton decay. So what these experiments were doing was measuring the background for their experiment very, very well, or as well as you can. And the anomaly that they discovered, the so-called atmospheric neutrino anomaly, that was actually reported by 2 different experiments. There's something called the IMB experiment in the United States and the Kameoka experiment in Japan. Basically, one measurement that they made was the following. So neutrinos are being produced in the atmosphere. That's the picture there. And of course, the neutrinos don't interact very much. So when you say a neutrino is produced in the atmosphere, as far as your detector is concerned, you care about the Earth's entire atmosphere. All of the neutrinos produced there will get to your detector. And there's a very simple prediction you can make, assuming that the neutrinos don't interact very much, that if you look at a solid angle upwards and you count how many neutrinos are coming from this solid angle upwards, and you ask how many neutrinos are coming from the same solid angle going downwards, you notice that even though those neutrinos are very far away, so not all of them will get to your detector, because it's a solid angle, the solid angle gets to be really big, right? So if I make a picture of that, here's the Earth, here's my detector. So if I look at how many neutrinos come from up here and how many neutrinos come from all the way down here, you can convince yourself that those numbers are supposed to be exactly the same. So if you assume that the production, or that the cosmic rays hit the atmosphere with the same flux from every direction, you expect the number of neutrinos from below to be the same as the number of neutrinos from above. The reason they were looking at things like that is because calculating the flux of neutrinos produced in the atmosphere is a very hard business. It's not an easy calculation. There are lots of problems, but you want to look for robust properties that this flux would have, and this up-down asymmetry is a very robust property. And that was what's written there in green. So you expect this up-down ratio to be 1, and when these experiments ran, instead of getting 1, they got a half. Okay, yes? Oh, that's a very good question. So, so the way those experiments work is this is a different energy regime. The biggest reaction that they're looking for is neutrinos, muon neutrinos hitting something, and that produces a muon plus something else. This is at high energy now. It's above 100 MeV. You're happy to produce a muon. And what happens is this reaction is also a very forward reaction for the muon. So you can measure the direction of the muon really well. So by looking at the direction of the muon, you can guess where the neutrino is coming from. There's some uncertainty there, but you can take that into account. So very good. That's what they were measuring. So the reason this is a very important result is because it's a very big effect. You know, an up-down ratio of a half. You know, if you got 95%, then you could say that something went wrong. But a big effect like that of a half is a very big deal. They also measured a couple of other things which I don't want to get into, but I do want to show the data. So they can do better than just looking at up and down. What they can do is they can measure the flux as a function of angle. So you can count, you know, how many neutrinos come from above, how many neutrinos come from over there, how many neutrinos come from over there, and so on. And all of these plots are measurements of this. And the distinction here is that they can tell electron neutrinos from muon neutrinos. So they can tell electrons from muons very well. So they separate the samples out that way. And the different windows here represent muon energies. And there are relatively low muon energies, there are pretty high muon energies, and then there's super high muon energies. So these are the three columns that go this way. And let's just leave it like that. There are other subcategories that we don't care about. What's really striking about this result is the solid lines are what you expect from everything that you know about cosmic rays. There's a lot of interesting things is that you notice that these plots are not flat as a function of cosine theta, although that depends on the energy a little bit. And there are different reasons for that. One interesting reason is the Earth's magnetic field. So the Earth's magnetic field will guide cosmic rays so that they hit different places in the Earth with different rates. And that effect depends on the energy of the cosmic ray. So if you're a super high energy cosmic ray, you don't care about the Earth's magnetic field because you don't get distorted very much. If the energy is lower, you get distorted much more. And as you know, cosmic rays like to do things around the North Pole, and then they do these pretty green lights and things like that. Okay, so that's one effect. The other one is if you look at the electron part of this picture, there's nothing very exciting going on. So the data are the points, and the solid lines agree with the points quite well. If you look at the muon part, the data and the prediction don't agree well at all. Okay, so that's the really important message of this measurement. And let me point out, for example, everybody's favorite curves are these. Did this die, or is it off? Oh, okay. Well, it doesn't matter. So if you look at the panels on the bottom, the second and third panels at the bottom, you notice that when you estimate how many neutrinos are coming from above, that's cosine theta close to 1. So cosine theta close to 1 are neutrinos coming from up there, and cosine theta of -1 are neutrinos coming from the other side of the Earth. You notice that you get the answer right for the neutrinos coming from above, and you get the answer wrong by about a factor of 2 for the neutrinos coming from below. That's the factor of 2, but you notice how much more information they have than just that. And the other phenomenon that you should notice is that the size of the effect depends on the energy. Okay? If you're curious about the panels on the right-hand side, these are more complicated because they only look at neutrinos coming from below. And these are neutrinos that have a lot of energy, and they hit something outside of the detector, and then a muon goes into your detector. And if the neutrinos are coming from below the horizon, it has to be so if the muon is coming from below the horizon, that can't be a cosmic ray. Cosmic ray muons cannot come from below the horizon. It's really, really hard because they would have gotten absorbed beforehand. Or above the horizon, even if you have a mountain on top of you, every once in a while a high energy muon can come through. But this is the really important result, and the key finding of this experiment is that neutrinos that travel a short distance agree with what you expected, and neutrinos that travel a long distance don't agree with what you expected. That's a very big problem, and people pondered about what was going on here, and I mean, again, everybody knows what the answer is, but if you look at a plot like this, what do you think is going on with these muon neutrinos? So just what would be everybody's sort of knee-jerk reaction? What's special about the neutrinos that travel a long time? Yeah, maybe they get absorbed by the Earth, right? That's kind of the logical explanation, but that makes no sense at all because we know how neutrinos interact. And it seems very unlikely that you would manage to absorb half of your neutrinos and still have enough neutrinos get to your detector, for example. And on top of that, we know a lot about neutrino interactions. It would require a gigantic new contribution to your cross-section for that to happen. But that's one logical possibility. The other logical possibility is that the neutrinos decay. right? You know, if something decays, that would explain why you're missing out on the component that traveled for a very long time. And there are other kinds of phenomena that other kinds of properties that you can give to your neutrino in order to explain why neutrinos that travel a short distance behave differently from neutrinos that travel a long distance. Now, there's a very, very general statement you can make, however, which is if you believe that your neutrinos can tell whether they've traveled a short distance or a long distance, then they must have mass. Okay? This is a very, very generic statement. And the reason is very simple. Maybe you've never thought about this, or you forgot that you thought about this when you learned about special relativity. But massless particles are very strange. Massless particles always travel at the speed of light, and they can't tell time. In their reference frame, everything happens always at the same time. So they don't have that concept. You know, there's no internal clock for a massless particle. As far as it's concerned, it's produced and it's detected, and everything kind of happens instantaneously in their reference frame. So if the neutrinos can tell time, which means that if they travel a short distance or a long distance, something different happens, that means that they must have mass. Or, if you're very brave, you can say that maybe a Lorentz invariance is wrong. And that would work too. And by the way, if you look at explanations for these data, these are the types of explanations you would raise. You can say maybe Lorentz invariance is wrong, and then you can explain these data. Or the neutrinos have to have some property that is associated with them having a non-trivial mass. So this is, again, another Nobel Prize winning experiment, probably for this plot. So that's their money plot, if you want. And they won it together with the Snow experiment for the discovery of neutrino masses. So any questions about any of this? So what I want to do now is to start talking about what's the solution or what's the explanation for all of these phenomena. I will not talk about all of the wrong explanations, although there were many, and for a long time they were a good logical possibility, but I do want to talk about what we are very sure is the right explanation. And the reason we know this is the right explanation is that we did many experiments after these experiments that I've just talked about to confirm that these hypotheses were actually correct. And they have to do with postulating that neutrinos have mass. Okay, so I'm going to go through this, probably not very, very slowly, but I'll try to emphasize the main ideas, and I will count on the fact that a subset of you have already seen this before, and I will count on the fact that everybody here knows quantum mechanics. That's all you need to know. Okay. So, here is the story. You can postulate what happens if the neutrinos have mass. Okay? If the neutrinos have masses and the masses are different, then you can label the neutrinos using the mass. Right? So, you know, there's one neutrino that has a certain mass, another neutrino has a different mass, and a third neutrino has a different mass. These are clearly different particles because they have different masses. So I can list my neutrinos that way. And the nomenclature that's been used, which is the most boring one, but that's the one that we're stuck with, is to label the neutrinos using a number. So the way that we do it is we say that, you know, one neutrino mass is M1, the other neutrino mass is M2, the other neutrino mass is M3. You can keep going if you like more neutrinos, but we're going to stop at 3. And then, of course, neutrino number 1 has mass M1, neutrino number 2 has mass M2, and neutrino number 3 has mass M3. Okay, so that's the definition of neutrinos with a well-defined mass. Of course, we've already gone through this exercise of telling the different neutrinos apart, and we gave them different names, which were the electron neutrino, the muon neutrino, and the tau neutrino. And these are also 3 different objects. Okay, and let's not get into the details. So the key question that you're supposed to ask yourself is, so which one is which? Right, so I have an electron neutrino, and you can say, is it this one, or that one? Or is the muon neutrino this one, and that one? Or is the tau neutrino this one, or that one? And the answer is yes. Because what happens is, this is quantum mechanics. So the electron neutrino doesn't have to be any of those, but it's a linear combination of those three states. A linear, quantum mechanical superposition of neutrino number 1, neutrino number 2, and neutrino number 3. The muon neutrino is also a linear combination of those three states here. And the tau neutrino is also a linear combination of those three states. Now, because the E, the mu, and the tau are different particles, or different states, then the electron neutrino is one linear combination of those three particles. The muon neutrino is a different linear combination of those three particles, and those linear combinations are orthogonal, right? Because the electron neutrino is not a muon neutrino, so this linear combination better not be the same other linear combination. They have to be perpendicular. And the same is true of the tau neutrino. The tau neutrino is a third linear combination of those three states, which is orthogonal to those two. So the shorthand for that statement is that equation at the bottom there that says that alpha is E, mu, or tau. So one of these neutrino alphas, which is a flavor eigenstate, is a linear superposition of the mass eigenstates, which are represented by these numbers U. U, E1, U, E3, U, mu2, and so on. These are the elements that define these linear combinations here. And of course, those linear combinations are all orthogonal to one another. So the consequence of this is the fact that this U defines a 3 by 3 unitary matrix. Okay? So is that very clear? Yes? Good. Why do we care about that? Because this hypothesis here can explain all of the data that I showed you so far. It's a very simple hypothesis. Yeah? That's exactly right. So I'll talk about that. So that's exactly the right picture. And that's all you need to know to understand what's going on until you start asking questions, and then we will get confused if we ask too many questions. But that's exactly the big picture. So that's what I say here. So the key point is what he just pointed out, which is, yes? It's the same as what you would imagine happens for the flavor eigenstates. And I'll just leave it like that. I think that's, so it's not, let me say something which I'll probably say many times before. Now that we've learned that neutrinos have mass, the particles that you should always be thinking about are the mass eigenstates. Flavor eigenstates are not particles. They don't really exist. Okay, they're not proper particles in the way that we like to talk about particles. Only the mass eigenstates are particles. Okay, how do we know that? Flavor eigenstates don't even have a well-defined mass. They're not the solution to any equation, because there's no Dirac equation that you can solve for something that doesn't have a well-defined mass. So they're not eigenstates of the free particle Hamiltonian. But everything that you normally think about for neutrinos in terms of properties, in terms of discrete symmetries and so on, you can apply that to the mass eigenstates. It's totally fine. And we can talk more about that in the questions, I think. Okay, so now that we've established this, you can ask, what's the yes? Yeah. Absolutely. Yes. Yeah, I'll talk about that briefly. That's a very good question. So I will point out at which point we are worried about this, and then I'll try to tell you what's the solution to that. And it's related to the fact that the neutrino masses are very small. So because the masses are very small, there will be a number of simplifying assumptions that allow you to assign an energy to what we normally call a mass and get away with it. But that's a very good question. Clearly, mass is not the thing that you care about, but you do care about the difference in the energies. And then you can ask, how can I have different energies? That's kind of the question. But I'll show that in the next slide. So any other questions? Okay, so before I go to the next slide, let me say what I was going to say. The key question is, what does it mean to be an eigenstate of mass? And it means very precisely that eigenstates of mass are solutions to the free particle, or they're eigenstates of the free particle Hamiltonian. So if I say I have a neutrino that's free of any interactions, and I ask what's the Hamiltonian for that one neutrino state, I can write that out. And then I can ask what are the eigenstates of that, and these are the mass eigenstates. Okay, so that's what a mass eigenstate is. And this is very important because that means when a neutrino is propagating, the objects which are eigenstates of the Hamiltonian are the mass eigenstates. So that means if you produce a mass eigenstate, and it would be nice if I had a pointer, but I don't. If you produce a mass eigenstate and you ask how does it propagate, quem sabe agora? Oh, now it works. Okay, good. So this is what it means to be an eigenstate of the Hamiltonian, right? You know, you're produced at t equals 0, and then you evolve, and your time evolution is trivial. You just get a phase and some e to the minus I et. And of course, the energy is your eigenvalue. Now, the eigenstate of the Hamiltonian is also described by a dispersion relation, which is a relationship between energy and momentum that looks like you know, what you learn in the Einstein dispersion relation. So E squared minus P squared is equal to M squared. And this is how these states here evolve. Of course, I can do this in a relativistic way, and my phase factors will look like some e to the minus IPX, where PX is the dot product of the four momenta. Okay? And so just go with me for now, and you can ask all the questions later. Because the important thing is the basic quantum mechanics. The details just make things confusing. But what are the flavor eigenstates? Flavor eigenstates are linear combination of mass eigenstates. And here I did it assuming that there are only two neutrinos because it's easier to write down unitary 2x2 matrices than unitary 3x3 matrices. Okay? So the idea then is that the electron neutrino is a linear combination of nu1 and nu2. The mu1 neutrino is a different linear combination of nu1 and nu2, and those two linear combinations are orthonormal. So that means that the bracket of a nu mu with a nu e is equal to 0 if you take into account that the bracket between a nu1 and a nu2 is also 0. And that the bracket between a nu1 with itself is 1, because that's a properly normalized state, and the bracket of a nu e with a nu e is also 1 because that's also a properly normalized state. Okay? So this is very, very important because the consequence of this is that the electron neutrino or the muon neutrino are not eigenstates of the free particle propagating Hamiltonian. So that means, and this is the key point, whenever I produce a neutrino, I have to produce one of these flavor states. But it's not an eigenstate of the Hamiltonian. So as it propagates, it doesn't have to stay a flavor state all the time. It can change, just like ordinary quantum mechanics. Again, this is the simplest quantum mechanics problem you can ever do. It's the two-level system. And hopefully everybody here is an expert on the two-level system. Because that's the one thing that you should learn really well in, you know, Quantum Mechanics 1. If you didn't learn that, you should go back and take Quantum Mechanics 1 again, because you want to learn that really well, because it's very, very important. All of quantum mechanics can be, that's not true, but a lot of basic quantum mechanics is understood just by understanding the system very well. You don't get to do entanglement because it's only one, doesn't matter. So that's it, that's all we have to do. Now the tricky part is how do you solve the problem? Well, you do it by saying that, you know, neutrino number 1 is a mass eigenstate. So when it travels in space and time, it picks up a phase. We're treating this as a plane wave. Neutrino number 2 is also a mass eigenstate. So it also picks up a different phase. And the thing that you care about is the difference in those phases. And that's what leads to the flavor change. It's because if this phase is not the same as that one, as you propagate in space and time, you acquire a phase difference. So that means that what you started out with, which was an electron neutrino, as time goes by, is no longer the electron neutrino because you get a different phase between the two components of your wave. Okay? So is everybody fine with that? So if you believe me so far, the question then becomes, what is this phase difference? And in particular, if I want to calculate something like what's the probability that a neutrino is born as an electron neutrino and measured as a muon neutrino? You start out with the electron neutrino, you propagate it until position L, so you get something that looks like this, and then you ask what's the probability that that's a muon neutrino. The key thing to be calculated is the phase difference, and this is where I will give you a hand-wavy answer for what the phase difference should be, and the answer is correct. The hand-waviness is not, but we'll just go with that. So one approximation that you make is that you assume that the neutrinos are traveling really fast. So the time that's elapsed between production and detection is the same as the distance between production and detection in units of the speed of light. So that's one assumption that you make. And then the other assumption that you make is that the energy and the momenta are very, very close to one another, in such a way that the difference between the energy and the momentum is proportional to the mass squared divided by the energy. Okay? So we can talk a lot more about this, and I'll probably talk about this in the questions, but just trust me for now. So what you were asking is, so what is my energy difference? The equivalence of my energy difference in this language is the mass squared divided by the energy of the neutrino. And because the masses are different, that's what characterizes my energy levels. It's the mass squared divided by the energy. Okay? So we can talk a lot more about this in the questions, but I don't want to lose the thread of the discussion. So just to say that in your quantum mechanics picture that you're making in your mind, the equivalence of the delta E is given by the difference of the masses squared divided by the energy. And you can ask which energy. It's the neutrino energy. And you can ask, is it the energy of neutrino 1 or neutrino 2? It doesn't matter because that energy is the same. Okay? So let's just swallow that, and then we can talk about that later. Okay? So if I do that, it's a very, very simple exercise to show that this probability is given by an expression that looks like this. This is the same as, say, Rabi oscillations in ordinary quantum mechanics that you learn about. And it's characterized by an amplitude, which is proportional to these elements of these unitary matrix that I defined before. And then there's an oscillatory pattern associated to that, right? And the frequency of the oscillation is proportional to the neutrino masses, the difference of neutrino masses squared. Yes? Almost. Because you also have to worry about the momenta. And the question is, what did I assume about that? And the answer is, I didn't tell you what I assumed. The key point is what you really want to calculate is the phase difference between those two things. And you know that the x's are the same. Or maybe you don't know that, but that's one assumption you have to make. And then you're calculating the difference of the one, in quotes, the difference of this dot product here from that dot product there. And that's what you're estimating. And I'm just telling you what the answer is for now. Oh, so that's easier to, so the idea is that the different mass eigenstates have different masses. That's what characterizes them. The energy and the momentum have to do with the production process. So for every given neutrino production process, the neutrino has a certain energy and momentum. The assumption I'm making is that those energy and momenta are very, very close to one another. So even though I'm producing neutrinos with different masses, you can convince yourself that, okay, so I'll talk about this. If I'm telling you that you produce a neutrino with a given mass from some physics process, it has a well-defined energy and momentum, which obeys a relationship that looks like that. If I produce a neutrino with a different mass, it will have a different energy and momentum. So how can I say that that I'm producing a linear combination of two things which have different energy and momenta? That's the key question that you'd like to ask. And the answer is you're allowed to do that because of the uncertainty principle. And that's what you're really using in order to justify that this makes sense. So again, it's the difference of it's the masses that characterizes the states, and the energies have to do with the process that you're interested in. So every different process has a different energy. The masses are things which are physical, associated with the physical states, and they don't change from process to process. Okay? So more questions. Yeah. Yeah. That's another very good question. The answer is yes. It's an excellent question because what you really have to do to make sense out of all of this is you have to define a one. So you can even ask about quantum field theory. But even if you care about quantum field theory, we're discussing a one-particle state. And a one-particle state is a solution to the Dirac equation. But the different components of your spinner, if you want to think about that, they will have a dispersion relation that looks like that, and their time evolution is given by the Schrodinger equation. That part doesn't change. You know, if it can obey the Klein-Gordon equation, the Schrodinger equation, the spin 3/2 equation. Nonetheless, Schrodinger time evolution of states is always the same. It's e to the minus I ht, and you have to figure out what the Hamiltonian is. So all of this is totally fine. However, the one thing which is important is that we would like to make this system look like a non-relativistic quantum mechanics system, and it turns out that it looks like that. That's a coincidence, in quotes. So the fact that it looks like a non-relativistic quantum mechanics, so the neutrinos definitely evolve in this way. That's not I'm not violating special relativity in any way. When I map this problem into a quantum mechanics problem, I got lucky that it happens to look like a non-relativistic quantum mechanics problem. So these are two different things that are going on, and sadly, it's easy to get confused, but that's a very good question. All right, so since I'm running out of time, and let me just say that this is what this curve looks like for the two-flavor system. And if you give me just a few minutes, I do want to go through how we solve some of the problems that I talked about. But this is a very important curve because it says this is how neutrinos oscillate. So that means you can be born as an electron neutrino and have a non-zero probability of being detected as a different flavor of neutrino. And if you think about that, that's mostly what you need to solve all these problems. I didn't talk about this in the context of the muon neutrinos or the atmospheric neutrinos, but a possible solution for why you're missing out on these muon neutrinos is that maybe they're converting into a different kind of neutrino. By the way, we know it's not the electron neutrino because the electron neutrinos don't do anything funny, so it has to be into a tau neutrino. Okay? But this is the main idea, and you notice that you have two phenomenological parameters, the delta m squared and the mixing angle. So these are the parameters that you can vary to see if you can fit your data. And that's what I'm going to show. I'm going to skip this curve here. So this is a summary of all things you should be concerned about this derivation. And I'm not going to read this, but we're going to talk about this later. I do want to show just how you solve the atmospheric neutrino problem, because that's easy. And in quotes. And this is also one of the exercises that I either gave you yesterday or I'll give you today. And the idea is very simple. So the probability that a muon neutrino stays a muon neutrino is given by an expression that looks like this in this two-flavor approximation. So let's assume that the two-flavor approximation works, because it turns out to be what happens. So that's the expression for the survival probability of muon neutrinos. And the question is, can I explain these data? And the answer turns out to be yes, because again, this depends on the distance. And what happens is, so if you look at this plot, these neutrinos travel a very short distance, and these neutrinos travel a very long distance. So how do I explain these data? For the short distance part, I just make sure that the sign squared is very small. So if I plug in a certain value of L, which is small, if the argument of the sign is small, this is close to 0, so the survival probability is 100%, and that fits my data very well. If I look at neutrinos that travel a very long distance, I have the sign squared of some very big argument, and then you can also convince yourself that these data are binned. So that means that you're combining different values of the angle. That means you combine different distances into the same bin. So what I really measure is the average value of this quantity here. And if the argument of the sign is very large, and you average over a range of arguments of the sign, you have a sinusoidal function, and you're calculating the average of that over many, many oscillations. The average value of that is 1/2. So that means that for long distances, the survival probability is 1 minus 1/2 of sine squared of 2 theta. So this is this behavior over here. I'm missing half of my neutrinos. So that means that I need this number sine squared of 2 theta to be close to 1. And then this number here is 1/2. So this explains the behavior over here. And this explains the behavior over there. I have to pick this number delta m squared. So I picked the number to be such that this transition happens over here in the middle. Okay? So by picking the value of delta m squared, I get this dotted curve that's right here, and you see that it goes right through my points. Now what's really impressive about this exercise is, first of all, you explain all of these data perfectly by choosing this number and that number. And what's really nice is once you've done that, you don't have any more numbers to pick. So now you have to explain all these other panels over here. And you notice that the dotted lines go through the points perfectly. And what's happening in these different panels is the energy is changing. So these different panels have different values of the energy. And since I've already fixed the delta m squared and the theta, the fact that I get a perfect fit everywhere tells me that I probably know what I'm doing. And that this is working very well. Okay? So this is how oscillations explain this, this picture here. And of course, we haven't done anything very spectacular because we only get to see these averaging out effects. There's one thing which you should complain about, which is this doesn't look like an oscillation in the sense that nothing goes up and down. It just goes down. But that's fine, and we'll talk about things that look like an oscillation the next time since I'm running out of time. But this is a very, very impressive fit. And the only thing that you want to be worried about is that I'm making this two-flavor approximation. Clearly, there are 3 neutrinos, so that approximation better not be entirely correct. And on top of that, nothing happens to the electron neutrinos. So when I say it's a two-flavor approximation, these muon neutrinos which are disappearing, they're disappearing into tau neutrinos. Because that's the, at least until this afternoon, when Orlando talks about stereoneutrinos, these are all the neutrinos we have, the mu and the tau. So if you're not disappearing into the e's, you have to be disappearing into the taus. So that's the interpretation here. Let me just very briefly talk about this slide, just to complete this thought, and then I'll stop. Of course, this is the hypothesis that you get out of the neutrinos coming from the atmosphere. What we managed to do in the last 20 years or so is to reproduce that in the laboratory. So the first 2 experiments that were designed to test whether this hypothesis was correct were the K2K experiment in Japan and the MINOS experiment in the United States at Fermilab. And they were designed to test if this interpretation of the atmospheric data was correct. And the way that they did that is they had a beam of neutrinos of the muon type. You shoot them over a very long distance. The distances, so we'll talk about that more the next time. Basically, for a 1 GeV neutrino, if you want it to oscillate, you have to wait about 1,000 kilometers. So these are kind of crazy experiments. But nonetheless, you can do the experiment, and these experiments confirm that the neutrinos do oscillate in this way as I've just described. And I'll conclude just by talking about these 2 plots. Like I said, when you do this fit, or when you try to explain the data, you're picking a value of delta m squared, and you're picking a value of the mixing angle. and then you say, oh, my atmospheric data likes to live in this part of the parameter space, this pink region. Then you do the experiment in the laboratory, and you also see an effect that's consistent with oscillations. And that experiment says, this is the K2K experiment. It says, oh, I really like to live in this region of the parameter space. The Minos experiment says, I really like to live in this region of the parameter space. And it's very impressive that the regions agree. So this is a very strong hint that you know what you're doing. So that the hypothesis that you've made not only explains one set of data, but it explains a completely different set of data in a very different environment. So that's why we're very, very sure that this is what's going on with the atmospheric neutrinos. What I need to talk about, which I didn't get to, unfortunately, is what happens with the solar neutrinos. And it turns out with the solar neutrinos, the story is harder. That's what I'll talk about the next time.
Okay, so unfortunately we don't have time for questions, but as Fabio says, please write down your questions, and we'll have time in the afternoon to ask many of them. And let's thank again Andrea. Thanks. Yes, so now we have the poster session. If people wanted to have a slide shown, they could send. Otherwise, I'll just post the title of the slides so that the person knows, so that we know the order. And it's just, the idea is just to advertise the poster, so each one will have 3 minutes to say what the poster is about. And during the coffee break, these are the posters that will be discussed, but also they are posted all the week, so we can discuss them at any time. But that's an advertisement. So I'll just open here. And I think the first person is Christopher Zuniga Vargas. Oh, sorry, not Christopher. Zuniga was only the rights. Ariel, I'm sorry. Ariel Zuniga Reyes. Okay, come here. Sorry about that, Ariel. So I'm just showing that. No, I'm not showing anything. Just showing the title of the poster. Thanks.
Thank you. Well, my name is Ariel, and I'm doing my PhD at the National Autonomous University of Mexico. And in this opportunity, I'm going to present a new kind of experiment, which is scintillating bubble chambers. Bubble chambers were invented in the middle of the past century. But this new kind of experiment, the new thing here is that these bubble chambers emit light. That is the new. Well, in this poster, first I'm going to explain briefly how a bubble chamber works. I put the PICO example. PICO is a bubble chamber which is taking data at the snow lab. That professor mentioned that experiment. And I'm going to explain how this bubble chamber works. Next, I will mention the first demonstration of this prototype of scintillating bubble chamber, which was a project developed by Northwestern University. And I will talk about the next step, which is make this prototype bigger using liquid argon. And in this project, I'm going to do my PhD. And to conclude, I will mention the main research capabilities of this kind of experimental facility that could serve for searching low mass WIMP in the mass range from 1 to 10 GeV, and also to detect the coherent elastic neutrino nucleus scattering.
I think the next one is from UNAM too. Yes, Brenda. That has sent the. Is okay.
Well, hello, I'm Brenda Cervantes. I'm also from UNAM, Mexico. And we are working in two main experiments that use CCDs as detectors. One is DAMIC, which searches for low mass dark matter. And the other one is CONI, which searches the interaction between neutrino and nucleus in a CCD. So what I did is mainly something about the calibration of the CCDs of these detectors. So first, we were interested in studying the channeling effect. That effect was published in some articles. That effect has to be with the direction of the incident particles. So we wanted to know if the energy spectrums produced in these CCDs are related to the incident direction of the particles. So that was important in order to distinguish some signals, especially from dark matter. So I did, many things. One was an experimental setup that I put radioactive sources, neutron sources, because the neutron interacts with elastic scattering with the nucleus. So I did something experimental. Also, I did some analytical calculus of the channeling effect to measure how much it will be related with the energy spectrums and a change of that. Also, I show something about the quenching factor, that the quenching factor is something that must be studied in a detector, because it is the ratio between the energy that the particle is deposited in ionization and the real energy of the particle. So you have to study that a lot if you want to characterize your detector. And in that part, I did like a verification of some results showed by DAMIC. And this is also work in progress, so I can talk about this. And finally, I show the experimental spectrums and how they fit with the simulated part and also the theoretical part that I did, with considering all these quenching factors and the channeling effect. And that's all.
So, next poster by Lucas Oliveira Quintino. June potential for supernova neutrinos.
Oh, my name is Lucas. I'm doing my PhD on Federal University of ABC, UF-ABC, and I wanna. It's important to emphasize that my poster is work in progress. So I wanna see what is the Dune potential for supernova neutrino, because a few seconds before the supernova explosion, neutrinos of all flavor are emitted carrying important information for physics neutrinos and science in general. So with this information, we can know, for example, how the supernova explosion, the mass hierarchy of neutrino. We can study how the shock wave travel inside this stellar matter, and a lot of things, a lot of things. So it's a work in progress, and that's it.
Thanks. So next is Jessica Nayeli Lopez Sanchez.
Well, I study in Benemérita Universidad Autónoma de Puebla. The name of my work is Contribution of a Z-gauge boson to the top quark decay. So the Z-gauge boson is a connection between standard model and dark matter models because of its couplings to the fermions in both cases. So we have studied the phenomenology of this gauge boson through a process with the top quark decay in a process with flavor changing couplings. So this process is described by two bubble diagrams, Feynman diagrams, and one triangle, Feynman diagram. With that, we have obtained the amplitude as well as the width decay using the Feynman parametrization methods. So this process is mediated by a gauge boson. We have considered the Z-gauge boson, and we have studied its physics through the Lagrangian density, which includes the current, neutral currents. And we have considered some things related to the coupling constants in models with an extended gauge symmetry. So with that, we could plot the branching ratio as a function of the mass of the Z-gauge boson. And this shows an improvement related to the model standard result.
So last but not least, Vitor Barreto.
Hi all, my name is Victor. I'm doing my PhD at Rio, FRJ, and I'm work for the DAMIC collaboration. DAMIC is a dark matter experiment installed at the Snow Lab, the same facility that held the Snow experiment. DAMIC employs science-grade CCDs. CCDs is just a good camera, digital camera, and use it as target to search for WIMPs. But as we have amazing energy resolution, we can also search for some exotic particles. So this is the work I will present. It's the constraints that we put on EEV scale hidden photons. So you'll see my poster later, and you can ask questions how DAMIC works and how we could place these limits.
Thank you. Just before we go to lunch, if any of you did not sign the presence sheet in the morning, please look for me. Actually, a few people are missing. And if so, we may upgrade those that we could not fit into the experiments. We can upgrade some of them at least to go to perform the full school next week. So this is why it's very important for us to know exactly who's here. So if someone is not showing up often, also he or she can be downgraded. But so we need to know if these missing people are really missing, and then we can offer this room for more people to attend the experiments, or if they are around. So if you did not sign up the presence sheet, please let me know. We go for lunch, and then we reconvene at 2:30. Thanks.